Jerry Agar continues. In-depth radio. News Talk 1010.
So I don't know very much about telescopes.
Hubble, its big advantage isn't its size, it's that it's in space. Hubble is a 2.4 meter diameter mirror. So this telescope, PMT, is going to collect 144 times more light than Hubble, and it actually is going to have 10 times the resolution that Hubble has.
The difference being, though, that it has to peer through the atmosphere first, whereas the Hubble doesn't have to do that.
Yes, but there's actually a new piece of technology that's just been around for a few years, actually, that's going to help solve that. That PMT is going to be the first telescope ever designed from the ground up to incorporate something called adaptive optics. And this is something that actually Canada has a great deal of experience in. It's something that we've certainly distinguished ourselves as a nation as being very good at. This is the first mission that we've been asked to participate in this way, and certainly won't be the last.
Anyway, there's so many mirrors here that it's not trivial.
You think you would ever get a parrot?
No. When I was growing up, I had a bird, pet bird, a myna.
Is that a kind of parrot?
No, it's a tropical bird. It can talk too. You can train it to talk a little bit. But we gave him away when we left Singapore.
Oh, yeah.
If we didn't like him that much. Well, we brought the dog though.
So this is our scaled down version of an adaptive optics system that would be present at a real telescope. And this is where we get to implement and innovate new ideas that would allow us to improve the limitations of standard adaptive optics.
And liftoff.
So with the success of JWST, a lot of people are wondering what's going to be the next big thing in astronomical instrumentation over the next few years. Well, in the coming decades, a number of ground-based telescopes are going to come online with 4 to 6 times the resolution of JWST. The additional resolving power is going to allow astronomers to image things like exoplanets with unprecedented sensitivity. And really, adaptive optics is the key technology that allows us to unlock the full potential of these facilities. Without adaptive optics, these telescopes wouldn't be able to resolve any more than a backyard telescope. So what we have here is 2 objects that are extremely close together. We have one that's brighter than the other. Maybe they're a binary system, or maybe this is like an exoplanet, or just 2 stars that are close together. And essentially we have right now, everything is perfectly flat and there's no turbulence from the atmosphere. So what we can imagine is that the light coming from these objects is a perfectly flat sheet of paper, and it's sort of wavefronts just coming from the object perfectly flat. And then what happens is when they hit the atmosphere, we can imagine that the atmosphere crumples up that paper, and we end up with a bunch of waves and divots in the wavefront. And so with an adaptive optics system, what we do is we have a mirror that can change shape and become the exact inverse of all of these tiny crumples and waves in the paper, so that when the wavefront bounces off the mirror, we essentially are just flattening out the wavefront the best we can to return it to its original shape. So if we add the atmosphere to our system right now, we can see that they sort of all get muddled together. So this is atmosphere just sort of muddling all the light together. And you can't really distinguish the 2 objects. But now, if we turn on adaptive optics, we can see all of a sudden, you can see there's another object there. And so that would be how you would discover 2 objects that were close together, or it just improved the resolution of your image.
While adaptive optics is powerful technology, it's not being used by astronomers as much as we would like, due to a number of reasons, one of which is sky coverage, where you don't have enough references in the night sky to measure the turbulence, and second, due to robustness issues where if there are variable conditions, it's hard for adaptive optics to keep up. So our group is building a new kind of wavefront sensor. It's an infrared pyramid wavefront sensor where we expect up to 10 times improvement in sky coverage over traditional systems, and also developing deep learning and machine learning algorithms that can help improve robustness of adaptive optics systems. Our plan is probably in August, September, this optical system that's being built will be taken to the University of Arizona, at which point we'll incorporate it into the MMT telescope.
The whole point of it is to actually detect and characterize the atmospheres of exoplanets. And you need adaptive optics and high resolution spectra to actually do that.
So it'll be a few months of work, and we plan on commissioning the system over the fall of this year. Better or worse?
Better. It's on the ground there.
Thank you.
Did you move forward or backwards?
I moved it back. This is way off. Is that good?
Too low.
So in our lab, we're building a near-infrared wavefront sensor, right over here, which is different from what's traditionally done, which is visible light wavefront sensing. And the reason near-infrared wavefront sensing is unique is that we can get better sky coverage because there are many more stars in the night sky that are brighter in the near-infrared.
So in order to actually get the detector to operate, it has to be housed in a cryostat chamber. So this is a vacuum chamber and a cooler, and it goes down to about negative 200 degrees Celsius. Now we worked on the hardware design and actually the creation of the cryostat, and we also worked on the actual readout electronics of the detector. In addition to that, we also wrote the code that controls the camera and actually what you do once you have images from the camera, how you read it out. I mean, looking at it from down here, you can see something's messed up. Like, it looks like it's not going through straight. Oh, you almost had it. Yeah, I can't see it.
You probably need to turn the
Turn
light
the
off.
lights off, yeah. Sorry, guys.
Oh no.
What? Oh no. That's not good.
What the challenge is when you build a camera like this, you have to really iterate and find all of the bugs in the design, both the mechanical problems. So this needs to stay under high vacuum, which means there might be leaks that you have to fix. And the electrical problems, we have to write software and do the cabling and electrical design, and there may be mistakes there. So there are often a lot of iterations, and this has basically been a few years of work to get it to this point. But now we have a camera that we've basically designed from scratch. We have some N2 here, probably means there's a leak, an air leak somewhere. What this guy's doing is trying to measure the mass of any kind of molecule or atom that comes off, and then it plots it in terms of pressure.
Where's the usual suspects where you think the leak would be?
Wherever the seals are, like there's a seal here, 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 and the window.
Nothing. There's a front. Oh, there you go.
Found a
That's
problem.
it.
It's
Found
our
it.
window. You see it just
Yeah.
bumped up at 4. I was wondering maybe it was the window,
There you
but
go.
it's pretty cool, huh? I've been in those situations where there's no idea where the problem is, and you're just trying everything.
And you spend hours.
Hours, days, and could be much worse. This should hopefully be a really easy thing to fix. Sometimes it feels like it's never ending. That's just how it is for astronomical instrumentation. It just feels like you're never going to get to that place. But there's always a point where you kind of turn a corner and things really come together. And it's been a challenging road because I'm wearing 2 hats. I'm an astronomer and I'm an engineer, and I have to straddle these 2 spheres. And it's hard to be good at both. And so, I have to kind of choose where I sit. So it's very painstaking work and careful work, but that's the nature of astronomical instrumentation. You just have to do that, and you have to have a love for that.
It's like, it's not relief, it's more just like you expect problems, and when you don't have any problems, you're not necessarily relieved, you're just like, that's good, you know?
Or sometimes you're skeptical.
Sometimes you're skeptical too, yeah. If everything goes too well, you're like, I don't know if it's gonna go that well. How does it work? Sorry.
Predictive control is a technique that lets us estimate what the atmosphere will look like in the future. Because all AO systems have a small amount of latency, there's a difference between the atmosphere that we measure and the one that we correct for. So if we can predict what the atmosphere will look like in the future, we can apply that correction instead and get better performance out of our AO system. Our method uses a history of atmospheric conditions that is already present in all AO systems, as well as some newer methods from computer vision and machine learning. Because we've set it up in this way, not only can our method be applied to new telescopes that are being developed now, but ideally they could also be used in previous telescopes and upgrade their performance without any costly hardware changes.
Okay, what is POL codes? Where does that go?
So this gets put into the history.
History.
Yeah, that's passed to the machine learning. Like first you get the wavefront sensor measurement, right?
Okay.
That's step one.
Let's say I have that. So let's say we have that. And then this turns into
the latest history entry.
So and then how do you get DM commands I? So then we just go DM equals C times
the CNN output.
CNN output.
Yeah.
When I do the history in my actual code, it'll be minus offset.
Yeah.
What space do you what do you need for the training?
Oh, well, the CNN's all in slopes.
It's all slopes.
Yeah.
So you need the history.
Yeah.
So that, fine tuning, normalization, and then we'll have to do a whole thing on experimental setup if we get that far.
Yeah.
I guess we go code now. All right. So if you see here physically, the light comes down and bounces off the mirror, and then it goes to our wavefront sensing cameras over here. Now, you have to actually expose for a little bit of time on those cameras, maybe a millisecond or so, and then compute a correction and then apply it to the mirror, and the mirror takes some time to actually get into the right shape. Now, that's what we call the latency of the system. The problem is, I can't do that because when the atmosphere removes the spots around. So I have to have it big otherwise we lose the ability to measure atmosphere beyond a certain quality. So what our predictive control does is we give a neural network a history of all of the wavefront measurements we've made in the past, few milliseconds, and then it produces a prediction of what shape the mirror should be in the future, so that by the time we actually apply the correction, the mirror is in the correct shape. And so what predictive control does is essentially it reduces the latency between when we measure the atmosphere and when we apply a correction on the mirror. But you can see this is the AO system noise. And then all the motion we're seeing is between, these are in pixel measurements. So it's 1/10 of a pixel we're seeing. But I'm gonna do a plot of the slopes. I want to see the variance. How many do you think we should draw?
Well, before it was like a steep decline. Here, I think it's probably like these ones, right?
Okay. So I could change that to being a square. That would just make my centroids much more accurate. Okay, we almost certainly have a working system, but do we actually have alignment?
Some of the biggest challenges for predictive control systems is how the atmosphere specifically is different between a simulation or even a bench setting like this one here and a real telescope. And for that reason, right now we've been installing a spatial light modulator. This is a spatial light modulator. We're able to use it kind of like a computer monitor. At each point on the little monitor, we can introduce atmosphere. And so instead of our phase atmosphere disk that we had before that would just rotate, we can put any shape we want onto the SLM.
Okay. It looks like it's not centered on the pupil for some reason.
Yeah, it does.
Do you know why?
I do not. That's the same shape that we're seeing there. Especially in machine learning, you have to be careful that you're not overfitting to the small amount of data that you have. So if we have something like this, we can put any shape on there, and so we don't run that same risk of repeating ourselves over and over again and learning just to regurgitate what we've already seen. That also means that when you're testing, you can be sure that you haven't seen that data before. And if the system works on this new data, you know that it would probably work on other new data, which is what we would see on a real telescope. Yeah, that's basically it.
Well, the really most exciting moment is when you build something, you put it on a telescope and you point it at a star and you get first light. That's got to be the most exciting thing, where you feel like it actually works.
What excites me most is essentially that all new ground-based observatories are going to need adaptive optics in order to meet their main science goals. And it's going to be, critical to the next generation of observations in astronomy.
I'll be really happy with the research until we actually have it, working on a telescope. I'm really proud of all the work that we've done so far, obviously, but that's kind of like the goal of my PhD.
So now when we're done here, we're actually going to take all of this equipment, the near-infrared wavefront sensor, to the University of Arizona, at which point we'll incorporate it into the MMT telescope. Myself and Jacob will be heading down there probably over the next several months as we incorporate this system into the telescope and commission it on Sky and get the adaptive optics system operational.
So this is the actual wavefront sensor that's going to be part of the adaptive optics system at the MMT Observatory. And actually right here is where our camera, the Saphira camera, is actually going to be mounted.
I want to take the opportunity to thank our collaborators who have contributed significant parts to our project. First of all, I want to thank the National Research Council of Canada, who helped us develop the infrared camera. And secondly, we would like to thank the University of Arizona, who is leading the project and we're working closely with. And finally, the MMT Observatory, who will be hosting our instrument.